design their routes. So I took NOAA's operational wave ensembles, and based on those I calculated uncertainties at all grid points at the 95% confidence level. And then I contoured those on top of the significant wave height forecasts. So the contours you can see here, the numbers are too small, but the contours you can see here are the uncertainties. So this way you can see more information. So let's say you have a forecast wave height of 5 meters for a certain location, and the uncertainty is plus minus half a meter. So it's a pretty certain forecast. But if you have the 5-meter waves at a different location with the uncertainty of plus minus 3 meters, a router would be much more hesitant to design a route through that area because there is a potential of having really high waves there. So it just gives the routers a bit more information about how confident they can be on the forecast. Moving on to this specific type of a wave that can be very dangerous to ships, namely rogue waves. And here are a few definitions for those of you who are not familiar with this type of a wave. So rogue wave is defined as a wave, the height of which is more than twice the significant wave height. And the significant wave height is the mean of the largest third of waves in a wave record. So rogue waves are not necessarily the highest waves that we find at sea, but they are unusually high waves for a given sea state. So that's the reason why they are really dangerous to vessels. And the generation process is really complicated. They occur as a sum of several different physical factors, such as high winds and strong currents. So how does AWT deal with rogue waves? Well, they developed many years ago a really simple model that it's designed to calculate the rogue wave risk for the kinds of rogue waves that are generated when the waves and the current are opposing each other. So we take the modeled currents and the current direction and the waves as input to the algorithm, and the algorithm then creates these different risk zones, high risk zone and a moderate risk zone. And I know it sounds extremely hand-wavy, and it is just that, but this model has been running for almost a decade now, and it has proven to be actually pretty good. Many times when there has been a rogue wave observation, our model has been able to catch that, meaning that the observation was inside one of these zones. And here is an example. We can display these zones on the map, so when the routers design their routes or the captain designs the route, they can try to avoid these areas. Well, I mentioned that we use modeled currents to get the rogue wave threat. Well, that is not the only thing we use currents for. I mentioned earlier in the presentation that no ship wants to sail against the western boundary current. So we get high-resolution current data from the real-time ocean forecasting system, RTOFS. And we can then display it here on the PBS display. And here is an example of the coast of Brazil, where there is a strong boundary current, and ships moving through this region, they always want to know where the strongest currents reside. What we see here is not just wind-driven currents. We combine the wind-driven currents and tidal currents. And for the tides, we run our own in-house model, which is the State University Tide Model. Here you can see the different regions that this tide model can be run for. We run it for these, I think it's 9 or 10 regions. And the output we get from these models, we then combine with the RTOFS surface currents and then place the combined currents in the PBS. An example of what the tidal currents look like on BBS. Obviously, no wind-driven currents here. This is tides close to the Straits of Gibraltar. And as you can see, BBS is not a good tool when it comes to checking out what the tides will be. Our resolution for tides is a quarter by quarter decree, and the time resolution is 3 hours, so not good for tides. So we need more specialized data products for tides for the customers who require such information. So for that purpose, I recently came up with little tide product. So the customers can give us information about waypoints along their routes. And my program takes in the waypoints and then calculates several tide-related things along their routes. So here, I know it's very small again, but you can see the route here. So the waypoints are here. And then my program calculates what the tide direction of the tidal current is, the strength, and the time when the ship is supposed to be in each of these locations. And then we have a time series for the strength of the tide, in this case every half an hour, and also the direction, and here is the height of the tide. So it just gives a bit more information to the ships what to expect along their route, more than what BVS would give by itself.
And do you give it a direction, the tide direction, or just a component along the ship track?
Yeah, there is both the direction, like it's difficult to see here, but there is an arrow here that gives the direction of the tide at each point. Ships that are sailing in the polar areas very cold, they often need to worry about something that's called vessel icing, meaning that the rate at which ice accumulates on the exterior of the ship. And here is an example, a pretty extreme example. So obviously ships want to avoid this. It's not an ideal situation. So fortunately, NCEP has a vessel icing model, which has been around since the 1980s. It takes the freezing point of seawater, the sea surface temperature, wind speed, and the air temperature as inputs, and then it calculates the something that's called the vessel icing threat, like how fast is the ice accumulating or the structure. And this is designed for ships like that are, let's see, from 60 feet to about 150 feet in length, that are traveling at normal speeds and not hitting downwind. And we update this data twice a day and then display it on BVS. So here you can see moderate icing conditions close to the coast of Antarctica. And one more ice-related thing. So obviously icebergs can be dangerous to vessels of all sizes. We all know what happened to Titanic. So we update this information once a day from the National Ice Center. So this area here with the red border gives you the danger zone for icebergs, and the gray area here designates the sea ice zone. And in the recent years, when the ice extent in the Arctic Sea has started to decrease, more and more ships actually use the northwest and northeast passages. So for that purpose, they often request sea ice concentration charts from us, and that's one of the products that I've quoted quite a few times for customers. So what have we learned? So I've shown you what the basic data needs are for a successful and safe voyage. We've looked into weather data, wave model data. We've covered tropical cyclones in depth. Then we've looked into ocean and tidal currents, and also some ice-related data. And I think a safe conclusion is to say that to guarantee a safe and cost-efficient ship routing solutions, high-resolution, state-of-the-art atmospheric and oceanographic model products are needed. That's for sure. And moreover, the demands for data are increasing all the time. The shipping companies want more data from us, and we need to be able to provide that. And in the future, one thing that's bound to increase is the use of ensemble-based model data. Just to estimate different uncertainties, and it will also be used for route optimization. And this is because the computation resources are increasing. So now these big centers like NCEP and ECMWF can actually run their ensemble models with high resolution and many ensemble members. So that use of that data is going to increase in the future for sure. So that's all I had for today. I'll be happy to answer any questions if you have some.